For centuries, humanity has dreamt of unlimited energy, free, clean, safe, infinite energy available to all. But in our rush to develop new power plants here on Earth, we keep causing damage to our planet and its atmosphere. So what if we went bigger, really big? Like how about building the single largest construction project in the history of the universe? What if we built a Dyson sphere? Welcome to my channel. It's time to learn how to build a star. Now, first off, in case you're not familiar with the concept, a Dyson sphere is a theoretical megastructure that completely surrounds a star, converting all of its energy into a usable form. But first, if you're enjoying the video so far or are new to the channel, make sure you hit the like and subscribe button. It really helps us out a lot. Alright, let's get back to it. But before we start wrapping up our nearest star and Christmas lights, we need to talk about why the hell would we want to do such a thing? Well, as much as the energy industry doesn't like to admit it, there's no real way to meet humanity's future energy needs without tapping some truly monumental power sources. Things like nuclear fusion, geothermal vents, or tidal waves are nice, but they just don't really scale all that well. And even if we harnessed every last scrap of solar energy that reaches the Earth's surface, we'd only be tapping about 0.00037% of the total power output of the sun. So now that we've established that yes, we will absolutely need something bigger, let's take a quick moment to visualize just how big. Our sun is massive, around 1.4 million kilometers in diameter. If we were to blow it up to the size of a soccer ball, a comfortable human skin distance away would be roughly 100 meters. Now, to put a soccer ball-sized sun in the center of a full-size Dyson sphere, we would need a megastructure around 27,000 kilometers in diameter. To give you a frame of reference, that's about 2/3 the distance between the Earth and the Moon. That's pretty damn big. Okay, so you might have noticed that a Dyson sphere is basically just a giant sphere. So the first step to building one would be finding a way to acquire a giant sphere worth of materials. According to one rough estimate, a Dyson sphere would need around 89 billion metric tons of material. For a little bit of context, the entire Tokyo Skytree, the world's tallest tower, weighs in at around 600,000 tons. So we're talking about a whole lot of metal. While the most abundant elements in the universe are hydrogen and helium, which aren't exactly super useful for building stuff, the next most common element is iron, which also happens to be really good at forming strong alloys. Unfortunately, iron is fairly rare on the Earth's surface, making up only about 5% of the planet's crust. However, thanks to humanity's relatively recent advancements in asteroid mining technology, acquiring large quantities of iron from near-Earth objects has become a viable commercial enterprise. One particular asteroid named Psyche is almost entirely made out of iron and nickel, and NASA has estimated that just that one rock could be worth over $10,000 quadrillion. So there's definitely no shortage of materials in the universe. It's just unfortunate that none of them seem to be located in any place that we can easily access. That's why the first step to building our megastructure would be a fleet of autonomous robotic miners that scour the inner solar system for metallic asteroids and bring them back to the assembly point. Once we have everything that we need, the next step would be figuring out how to build anything at all in space. We've done it before with the International Space Station. Sure, but that thing is basically just a glorified tin can by comparison. And it took a lot of expensive rocket launches to construct it. Thankfully, modern robotics and artificial intelligence have advanced to the point where we can send swarms of small autonomous builders into space that could operate with very little direct supervision. These little bots could each carry relatively small amounts of resources and then assemble them together to form larger structures until eventually you get something that looks like a gigantic Lego set in outer space. As these bots assemble the scaffolding of our Dyson sphere, we need to make sure that they don't burn up in the process. Stars are hot. Our sun blasts out around 382,000 watts per square meter of energy from its photospheric surface, which is about 1,000 times more energy than the Earth receives from the sun. If we harvest all of that energy and try to use it to power the grid, it would effectively kill everyone on the planet within seconds. So obviously, we'll need to find a way to radiate away all that excess heat. One possible solution would be to line the interior surface of the Dyson sphere with a reflective coating that bounces all the light and heat back towards the star. But then you run into the risk of overheating the star and sending it into a supernova. So instead, we'll need to develop an entirely new type of radiator that can safely dissipate heat while simultaneously collecting energy, maybe something that uses superconducting circuits or quantum effects. Yeah, that sounds like a hard engineering problem that I'm totally not qualified to comment on. Of course, even once we've figured out all of the easy problems, we still need to contend with gravity. Stars are also very, very heavy. Our sun makes up 99.8% of the mass of our solar system and exerts a gravitational force around 330,000 times greater than the Earth's gravity. Not only does the Dyson sphere need to withstand that crushing pressure, but it also has to deal with the sun's intense magnetic fields and solar winds. One potential solution would be to build a rigid shell around the star that's made out of incredibly strong carbon nanotubes. Another solution would be to create a swarm of smaller craft that individually don't experience the same gravitational stress, but collectively form a coherent sphere. Either way, we're going to need some physics that's not currently possible. And finally, keeping the Dyson sphere in orbit around the sun is another monumental challenge. Stars tend to emit a tremendous amount of energy in random directions. It could throw the entire megastructure out of whack and cause a catastrophic collision with Mercury or Venus or something. To prevent that from happening, we'll need a sophisticated system of thrusters that make tiny adjustments to keep the Dyson sphere in perfect balance. Basically, a million tiny orbital mechanics engineers working in unison to keep everything glued together. But hey, what about the sun's perspective? What would happen if you tried to wrap a star-sized ball of plasma in a blanket? Well, stars are born out of collapsing clouds of gas and dust. As the particles collide, their kinetic energy transforms into heat and radiation. Stars spend the majority of their lives fusing hydrogen into helium in their cores. When the hydrogen runs out, the core collapses again, heating up the remaining helium to the point where it fuses into carbon. This process repeats several times until the star has exhausted all of its available fuel. At the end of its life, a star will either explode as a supernova or collapse in on itself and become a white dwarf. If we completely encase a star in a Dyson sphere, we would cut off the star's supply of hydrogen fuel and cause it to go out like a candle. The star would slowly cool down and over billions of years turn into a faint white dwarf, so at least we wouldn't trigger a supernova. While all of those engineering challenges are certainly daunting, there are some equally difficult hurdles that have nothing to do with physics. Even if we overcome all of the technical difficulties and figure out how to build an actual Dyson sphere, who would own it? The United Nations Office for Outer Space Affairs has already established a legal precedent that any celestial body discovered by a country automatically becomes the property of that country. But when it comes to a space-based Dyson sphere, that principle gets a little shaky. Would it be considered the property of the country that supplied the materials? The people who did the labor? The corporation that profited from selling the energy? There's no existing legal framework for dealing with a situation like this. So, we would need to establish a whole new set of geopolitics. Then there's the problem of resource allocation. In order to build a Dyson sphere, humanity would need to unite under a single banner and pool every last shred of our collective resources. We'd need to abandon petty squabbles and petty wars and work together as one species. You know, kind of like the real reason why the Death Star was such a bad idea. But perhaps the greatest hurdle of all would be convincing everyone that this is a good idea. Building a Dyson sphere would undoubtedly pose some level of existential risk to the planet and its inhabitants. If anything goes wrong, we could throw the entire solar system into chaos or destroy the sun, which would probably kill us all. There's also the risk that our efforts would be in vain, and humanity would wind up spending trillions of dollars developing technologies that never pan out. So maybe instead of building a Dyson sphere, we should focus on searching for other people's Dyson spheres. The argument goes that if any civilization out there is advanced enough to harness a star's energy, then they would also be advanced enough to develop powerful technologies that could detect from far away. With a little bit of effort, we should be able to spot Dyson spheres orbiting nearby stars, and once we do, we can study them to see if they present any unique opportunities for interstellar exploration. In 1964, Soviet astronomer Nikolai Kardashev proposed a method for measuring the technological advancement of civilizations. Kardashev labeled these levels types 1, 2, and 3, with type 3 representing the ultimate technological achievement. A Type 3 civilization would have harnessed the energy of its entire galaxy, putting them thousands or even millions of times more advanced than we are. If we ever discover evidence of Type 3 civilizations, then we might have a chance to learn how they accomplished such a monumental feat and potentially reverse engineer their technologies. Maybe someday in the far future, we could unite the galaxy to build our own Dyson swarm and reach Type 2 status. Then we can move on to harvesting the energy of our entire galaxy and become Type 3. In the meantime, though, we should focus on smaller goals, like powering our solar system. The good news is that we've already started on our journey. Solar power is becoming more efficient and more affordable every year, and there are companies out there who are testing designs for giant solar farms in space. Someday in the future, we might even build something close to a full-scale Dyson swarm. But that day is still far off because there's a lot of physics that we need to solve first. If you want to help us make even more great space videos, then consider supporting us by hitting the like and subscribe button down below. And as always, keep looking up.